Alright, so in this problem we're again going to be looking at one of these classic optimization problems, except for in this problem we're going to be actually looking at trying to minimize something. And the thing we're going to be minimizing in this problem is actually going to be related to cost. So the situation that we're going to have here is going to be all around this idea of I'm going to be trying to build some box. In this case, this box is going to have a square base and it's going to have a specific volume. In this case, I need this box to actually have a volume of 343 cubic inches. So hopefully when you read that or see that idea, hopefully some kind of alarm about, hey, this is going to be the constraint, are starting to fire. And that's exactly what's going to happen in this situation. I'm going to build some function for the cost of this thing. It's going to have both x's and y's floating around, and then I'm going to have to use this constraint to actually pull everything back to actually build a nice little cost function that just has x's. I do all of my calculus from there and clean everything up from there. Okay, so what I'm going to have in this case is I'm going to have a specific set volume, and that's going to be 343 cubic inches. And then the other part of this component is that the sides of this object are going to have different prices. In this case, what I'm going to have is that the base of this object is going to be a little bit more expensive than the sides. If you think about this as kind of classically phrased as kind of an aquarium sometimes, if you think about the base of an aquarium, that's going to be made of some kind of slate or something like that, whereas the sides and the top may be constructed out of glass. And the price of that slate is going to be slightly different than the price of that glass. So whatever type of situation you're thinking about kind of setting this in, the idea is that the bottom is going to cost a different price than what the sides are. In this case, the top part and the sides are each going to cost a price of $0.02 per square inch, or just in this case, 2 cents per square inch, and the material for this base is going to be a cheap just 4 cents per square inch. So I kind of have two different prices going on. I'm going to try to merge all of this stuff in to create a nice little cost function. I did go ahead and start to construct a little image of what's going on in this case. So what I'm going to have is that down here is my base. I'm going to identify this as a slightly different color to kind of really show that that's going to cost a different price. And then the sides of this thing I've just kind of left open, and I'm going to identify the overall height of this object with a y. So if I tried to build the cost function, what's going to happen is that I'm going to think about taking these kind of different sides, these 6 different sides, and trying to add them all up. What's going to happen is that I'm going to have the bottom part and the area of the bottom part. So this is going to be the base. The area of the bottom is just going to be an x squared. And the price of materials for those things down there are going to be 4 cents. So I'm going to throw on the little factor of 0.04 out in front of that x squared. What's going to happen is I'm going to do the same thing to the top part. The top part's just going to be an area of x squared, but the kind of weight that gets thrown out in front of that thing is going to be a 0.02. So that's counting for the top part, it's counting for the bottom part. What I'm going to have in the middle of all of this is going to be basically 4 pieces, all of those pieces of which are going to have an area of x times y. So I have an x times a y, and I also am going to have a 4 in front of that to represent the 4. And then the very last part is I'm going to have the price of that component, which is going to be the same as the top, which was that 0.02. In this case, if I try to clean this up a little bit, what do I have? I have a 0.04x squared. That's going to give me this price of the materials for the base. What's going to happen is that that middle term is going to be this 0.02 multiplied by this 4, which is actually going to turn into a 0.08 xy. And the very end I actually had a 0.02 and it was an x squared, so I can actually lump that into that very front part, creating a 0.06. So that's going to be my cost function that I'm going to try to, in a sense, minimize at some point in time in this case, because that's what I want to do. I want to do this box most efficiently. And the situation of efficiency here is going to be, let's make this thing not cost that much. Let's do this as cheap as possible. Okay, so what I do have is an annoying situation where I do have 2 different variables going on. I do have both an x and a y making an appearance in this problem, and that's going to be something that's annoying. I don't really want to work with that. I want to somehow get around with that, but that's where the idea of this constraint is going to come into play. I haven't used that fact yet, so I do want to bring that back into play. So what I want is I want that the volume of this object is going to be fixed, and that volume has to be 343 cubic inches, which in this case is going to say the volume is 343, and I know what the volume of this cubic object is. It's going to be this idea that I'm going to take the length times the width times the height, which in this case is going to be an x times a y, and I'm setting that equal to 343. What I can do next is I can actually solve this thing for y, which is to say y is going to be 343 all over this x squared. So now I have this object that I actually know what y is going to equal. I'm going to take that thing and stuff it back into that y expression. What's going to happen is I'm going to get a nice little function that just has x's, and then I can do all the calculus that I ever want to on that thing. So what's going to happen is I'm going to have my cost, which I'm actually going to fully make kind of known that it's a function of x now. There's a 0.06x squared plus a 0.08x, and then I'm going to pick up a 343 over an x squared. If I clean this up even a little bit more, I'm going to have a 0.06x squared. If I multiply that 343 with that 0.8, I'm going to get something like a 27.44. And what's going to happen on this bottom part is I have one x up on top, and I got an x squared down on the bottom. What's going to happen is I just have one single x making an appearance, and it's actually going to be on the bottom. So I could write that either as a division by x, or what I could do is I could write this as an x to the negative 1. And I'm actually going to choose to write this as an x to the negative 1 because it makes my life a little bit easier when it comes to actually differentiating this thing. So that's the setup. I have this object, and I want to minimize this thing. The thing that's slightly different about this problem compared to some of the other ones is that I'm not actually going to be minimizing this thing on some nice fixed interval. I don't really have an official kind of, I know for sure that my x's should be some kind of bounded region. I know that my x's should at least be positive, but I don't really know an overall kind of nice upper limit on this. It's not as easy to see, so I'm just going to leave this as a giant kind of open interval. I'm just going to do a classic first derivative test on this thing. So I'm going to find my derivative, and then I'm going to evaluate it at around kind of a couple different points from that single critical point I'm going to see. So it's a slightly different approach just because I don't have this nice closed interval to work with, but the idea is going to be very similar. Still differentiate it, still find a critical point, but the way I test that critical point is going to be this classic first derivative test. So that's what's going to be up, is I have to actually differentiate this object, so I got to find out what the derivative of this thing is going to be. What I'm going to see is that c prime of x. What's going to happen is I'm going to differentiate this first component, which is going to say 0.06 multiplied by the derivative of this x squared, which is going to turn into a 0.12x. That second part, if I kick out that negative 1 out in front, it's going to be a negative 27.44, and then it's going to be an x to the negative 2. Like I said, what you could do is you could write this as a 0.12x and then a negative 27.44 all over an x squared. Well, in this case, we're going to think about two different situations. I got to think about when is this derivative going to equal 0. So that is, when is c prime equal to 0, as well as when does c prime of x not exist. In this case, the not exist one is actually the easy question to answer because you can see if x is equal to 0, I do in fact have this division by 0, and that's something I want to avoid. I can't divide by 0 in this situation, so I'm going to pick up a critical point at x equals 0, which is slightly different than some of the other ones because we've classically been just dealing with nice polynomials, so everything was kind of nice when it came to the derivative. In this case, I do have this division by x, so I do have to make sure that I'm not dividing by 0 in this situation. For the other thing, I do have to look about when is this thing going to actually equal 0, so I do have to solve this equation 0.12x minus a 27.44 all over x squared, and I want to know when this is equal to 0. What's going to happen is I'm going to bring this expression over to the right-hand side, which is going to say 27.44 all over x squared, and then I'm going to multiply that x squared over and then also divide by that 0.2, giving me that x cubed is going to be a 27.44 all over a 0.12. And if you take a cubic root of both sides of this thing, you're going to see that x is actually going to end up becoming the cubic root. If I actually write this as a decimal, it's not overly great to write as a decimal, I guess, but it's something a little bit easier to look at. It's a 228, and then it's actually a 6 that's repeating, which is actually, in this case, the cubic root of 686 over 3. So I didn't choose overly great numbers to start this thing off, but it's an okay expression to work with. So I got this kind of key x value that I'm looking for that's claiming to be hopefully the minimum in this case because it's only the one critical point I'm working with. If it's not the minimum, I guess I kind of have to go back to the drawing boards. But what I want to do is actually want to test that thing to actually show that it's actually going to be the minimum. I'm going to kind of do that over the top of this graph just because I ran out of room in this case. So what's going to happen is I'm going to create my little table of values. There's going to be an x here, and then I'm going to think about what is the sign of my derivative. In this case, what is the sign of my derivative? In this case, what is c prime's sign? So the sign of c prime. I'm going to choose my two critical points that I saw. There's going to be one here at 0, and there's going to be one at this kind of somewhat unpleasant cubic root of, in this case, 228.6, 228.6. What I'm going to do is going to think about taking a point to the left of that thing and a point to the right of that thing. Let's say take a point to the left of this object and kind of to the right of 0. An easy point to do would be to grab a 1. And if you grab a 1 in this thing, it's pretty easy to work with. What you could do is just take that 1, you plug it back into this derivative that you see over here. What's going to happen is that you most certainly are going to end up with a negative value. You're going to get out basically a negative 27.44 from over here, and then this 0.12. So it's definitely going to be negative to the left of this object, so my derivative is negative, 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 negative. And to the right of that object, if I choose a number bigger than this cubic root of 228.6 kind of repeating, what's going to happen is that my derivative is always going to be positive after that. So I do classically see that I'm going to be going from decreasing to increasing, which is representing that this point is actually going to go ahead and give me this minimum. And so I did kind of cheat because I see the graph of this thing sketched out below, and I do properly see that that point is in fact a minimum in this case. I have this value which as a decimal is about 6.115, and that key x value is actually going to give me my minimum amount of cost. In this case, the minimum cost is going to then be $6.73. So to kind of create this small little object, it's not overly big, it's only 343 cubic inches. It's got a kind of a small little base in this case, and the minimal cost for this thing while still achieving this volume of 343 cubic inches is actually going to be $6.73.